work done in an isothermal process. Okay. Consider ideal gas which is allowed to expand quasi-statically at constant temperature, but the both pressure and volume will be changes. Okay. So initial pressure is say Pi, then volume is Vi. So Pi, Va are the initial pressure and volume of the gas. Okay. Then after in the expansion, it will change as the final pressure is say Pf, and final volume is say Vf. Okay. So here the work is done. Okay. So we have to find the work done by the gas during this process. Okay. That we know the work done formula W is equal to what? Integral of Vi, then Vf, that is the limits, then pressure into change in volume. Okay. Put the equation number 1. This is the formula for the work done. Okay. You know that from ideal gas equation, PV equal to mu RT. PV equal to mu RT. This is the ideal gas equation. So we want P only here. So bring the V multiple, come with divide here. So we let us P is equal to mu RT by V. Put the equation number 2. Now we have to substitute the second equation, pressure, in the first equation. So substitute the equation 2 in 1. So we have work done is equal to limits of Vi, then Vf, then P again we will write as mu RT by V into dV. Here volume is only the variable, other thing mu RT are constant, so take note of integral. So we write as W is equal to mu RT integral of Vi, Vf, then dV by V. Okay. So in iteration of this dV by V, we get in the log formula. Okay. But log means we have put in base 10, so directly we put ln. Okay. So we get the iteration of this dV by V, we get in the ln value. So that W is equal to mu RT, then ln of upper limit now this Vf by lower limit is Vi. Okay. So this is the work done formula for that isothermal process. Okay. So based upon the value of Vf, Vi, you can say work done is positive or negative. Okay. So during an isothermal expansion, if the final volume will be greater than the initial volume, so that Vf by Vi is greater than 1, so that the ln value of Vf by Vi is greater than 0, so that work done will be positive. This is case 1. Okay. During that isothermal compression, the final value will be produced. Okay. So that Vf by Vi is less than 1, so that ln of Vf by Vi is less than 0. Okay. So in these cases work done will be negative. Okay. So you can assume that if in isothermal expansion means W, work done by the gas, is positive. In isothermal compression, the work done will be negative. Okay. Next we will see that work done in the adiabatic process. Okay. The graph shows that work done in an isothermal process. Here initial pressure Pi, volume is I think Vi is a volume. Okay, during that expansion volume will be increases, pressure will be decreases. So this is the final position. Okay, so T is constant for the isothermal process. So this is the region is called work done by the gas. Okay. In case of for the compression, initially here Pi, Vi, during compression the volume will be reduced, the pressure will be increased, so we get a curve like this, and T equal to constant for the isothermal process. So this shaded region is called water by the gas. Here water is positive, here water is negative. Okay. Next we will see that work done in an adiabatic process. Okay. Here the temperature is not constant. Okay. In case of isothermal process, temperature is constant between the surroundings and system. Okay. Is the temperature is not constant, so we write that the work done formula. Okay. W is equal to VI VF P into dV. The equation number 1. Okay. From the adiabatic condition, we will write as PV power gamma is equal to constant. Okay. So in this relation we will write as the V1 P now. So P is equal to some constant by V per gamma. Okay. Using this thing, you will write as for initial and final volume of pressures. So we will write as Pi Va per gamma is equal to Pf Vf per gamma is equal to constant. Okay. So put the equation number these two. Now substitute in the first equation. So we have work done is equal to integral of Vi Vf. P will write as constant by V power gamma into dV. Okay. So bring the constant in out of integral. So we'll write as W is equal to constant integral of the limits VA and VF. The power gamma, okay, in comes in the numerator become minus. So we'll write as V power minus of gamma into this dV. Okay. After integration, the form of integration of x power n into dx is equal to, okay, x power n plus 1 by n plus 1. The power is increased by 1, then divide. Okay. Here we have the same thing. So W is equal to constant of, okay, then V. So this is n means put plus 1. So minus gamma plus 1. Okay. Minus gamma plus 1. Same thing, what the power is same thing coming in diameter also, minus gamma plus 1. Okay. Then limits Vf Va. After integration we put the limits on the right side corner. Okay. Now we have to bring this term outside. Okay. So we write as W is equal to constant. So here minus gamma plus 1. I will write as 1 minus gamma. Okay. Now bring this, the power comes in diameter. So we have this numerator only. So I will write as 1 by V power. So numerator come in the diameter means just changing the sign. So minus become plus. Okay. So put gamma. Plus 1 become minus 1. Then upper limit Vf, lower limit Va. Okay. Here you take the common out, then write as 1 minus gamma. Same time the numerator become diameter means just change the sign of the gamma and 1. Okay. Then W is equal to now we have to bring the constant into the bracket. So 1 by 1 minus gamma, bring the constant into the bracket. So write the constant. Now apply the limits. So Vf minus Vi, upper limit minus lower limit. So constant of the upper limit what? We will write as Vf power gamma minus 1. Upper limit minus of lower limit means put constant by Vi power gamma minus 1. Okay. The constant value here is what? PAV gamma is equal to PFEF gamma. This is for initial, this is for final. Okay. Now we have to substitute the constant value here. So 1 by 1 minus gamma. For final, we write as this thing. So we write as Vf per gamma by, at the same time we have to separate the powers as Vf per gamma into Vf power minus 1. Here also for initial means Pi Va gamma. So put Pi Va gamma per gamma. Then similarly Va gamma into VI power minus 1. So VF gamma cancel, VI gamma cancel. So we have 1 by 1 minus gamma. Only we have PF. The VF is minus here, come with the plus in the denominator. So that is PF VF. Okay. Then minus of here is what? PI, right? VI. Okay. So now we have the work done formula is equal to 1 by 1 minus gamma of PF VF minus PI VI. Okay. From ideal gas, we know the formula what? PV is equal to mu RT. Gas of initial means PI VA equal to mu or constant only TI. Same PF VF is equal to mu or TF. Okay. So applying here for the PAV, we will write as W work done is equal to 1 by 1 minus gamma. Then we will realize what is the final here. VF means we write as mu or TF minus of mu or TI. Okay. Usually we have initial minus final only formula. Just interchanging means to take the minus is common out, put minus 1 by 1 minus gamma. Mu is common, take note mu or. Then remaining we have minus common means put thing here Ti first minus of Tf minus Ti minus plus Tf. Okay. Now bring this minus into the denominator. So I will write this here. W is equal to mu or. Minus goes here means plus become minus become plus. So I will write as gamma minus 1. Gamma minus 1 into Ti minus Tf. Okay, so this is the formula for the work done by the gas during the adiabatic process. Okay. Now we'll see the graphical representation for the work done by the gas in case of adiabatic expansion compression. First we see the expansion. Expansion means pressure will be reduced, volume will be increased. So the initial pressure volume here. This is the final volume pressure here. Okay, here T is reduced. Okay, so it's called initial temperature. Here it's called final temperature. So in case of adiabatic expansion, Ti is greater than Tf, so W is positive. In case of adiabatic compression, this is the initial pressure volume here, is the final volume pressure here. Okay, so this is compression means volume will be reduced, pressure will be increased. Okay, in these cases Ti is less than Tf. Okay, so W will become negative. For the expansion is work done will be positive. For the compression is work done will be negative. For both cases of adiabatic and isothermal process. Okay. So this diagram shows that how to understand the adiabatic process, which means the temperature is not constant for the system to the surroundings. Okay. So here the process occurs very quickly. When you wheel of the tire of the car will be suddenly burst means it will be the temperature comes out. Okay. When the tire bursts, the air expands inside the tire tube. It will be so quickly that there is no time to exchange heat with the surroundings. So it will be burst suddenly. Okay. So this is the example of the adiabatic process. This means the temperature is not constant for between the surroundings to the system. Okay. Next, this diagram shows in adiabatic compression the temperature increases. Okay, let's see. So this is the meaning of diesel engine working principle. Okay, so when you piston, this is a piston, this is a test tube, you fill it with the diesel air. Okay, the piston is compressed so quickly. Compressed means pushed downwards. Okay, that there is no time to exchange heat into surroundings. So when the pressure is increased means temperature also increases. Okay, so inside the pressure is increasing pressure, there is not time to exchange on the outside with the system, with the surroundings. Okay, so that the increased pressure is placed inside the tube. Okay, temperature is not same to the surroundings. Clear? So the temperature of gas increases rapidly inside it. So this principle is used in the diesel engine. So when pressure is increased inside it, it producing the heat energy, temperature is increases so that it will be burned. Okay. Yeah, this principle is used in the diesel engine. The air gasoline mixture is compressed so quickly. It's called adiabatic compression. The temperature is inside is increases enormously, which enough to producing a spark. Then the engine will be start. Then it will go the work function. Okay.